we've been talking about the substitution rule, which is a rule to do antiderivatives or definite integrals. And it's basically a form of, reversing the chain rule. The idea with the substitution rule is that we've got some sort of complicated integrand. And, we're hoping is it possible to do a variable change and make the integrand look a lot simpler? So in this particular integrand here, if we let u equal g of x, then du will look like g prime of x. And we can rewrite the integral as integral f of u du. And hopefully now, the whole point of this u substitution is hopefully now we've ended up with a simpler integral that's easier to find the antiderivative. So hopefully integral of f of u du is something we can do easily. The only other variation is when we have a definite integral and we have bounds. It's important to change the bounds if you change the variable. So if I go from the x variable to the u variable, then I need to use the u substitution to update the bounds so that they're also in the u variable. And so really the best way to talk about this is to show you examples. So this is the example, the last example we did last time, but I wanted to go over it again really quickly. So here we have an antiderivative problem. Remember, the integral of the product is not the product of the integral, so I can't just integrate each piece separately here. Here, I want to make the integrand look simpler. And so this is my motivation. This complicated part here that's x squared plus 7 that's inside the cube, if I call this x squared plus 7, if I replace that with a single variable, then the integrand suddenly starts to look simpler. Okay, and at the end of the day, certainly trial and error is involved. If the u substitution doesn't work out, we go back and start again. So in this case, motivated by the idea of trying to make the integrand look simpler, I'm going to let u equal x squared plus 7. And one very important thing to mention about u substitution is when we do a u substitution, we have to make sure to convert the measure, the dx here. We have to take that into account. That also has to be converted into a du. Okay. So typically when I write down a u substitution, the very next thing I'll do is write down what the du is. So here, just using differentials, du would be the derivative of x squared plus 7 is 2x dx. And so now in this integral, we get lucky. We have all the parts we need. I have the u is right here. And if you look outside, the 2x and dx we have. And so the 2x dx, I'm going to end up replacing with du. The x squared plus 7 that's inside the cube, I'm going to replace with u. And then we end up with this very nice transformed integral. And you'll see antiderivative of u cubed du is a lot simpler than antiderivative of 2x times x squared plus 7 cubed dx. But all we've done here is a cosmetic change. We've changed the variable so that now it looks different. And now we can use the power rule to find the antiderivative, power rule for antiderivative. So u to the 3 plus 1 divided by 3 plus 1 plus c. And then finally here, because the original problem was given to us in the x variable, I want my answer to be in the x variable. So I plug in the x squared plus 7 for u. This letter u here gets replaced with x squared plus 7. So I also did this same problem in a slightly different way. It's still a u substitution. We're still using the same u equals x squared plus 7. Then we get du equals 2x, du equals 2x times dx. And now this is the part that's slightly different. So now one could solve for dx. And so how does this work? Now when you're doing your substitution, we directly substitute for dx. We replace dx with du over 2x. The x squared plus 7 as before we're going to replace the x squared plus 7 with u. And the 2x now, you know, we notice it'll cancel with the 2x in the denominator. So after canceling top and bottom, we arrive again at the same, you know, simple form we had before. We end up here at antiderivative of u cubed du. So it's still the same u substitution. And of course, you take the antiderivative and you get the same answer, plug in for u, what we originally substituted, and you of course get the same answer. The only difference here is just a stylistic difference. Whether you want to solve for dx or manipulate the integral so that you can plug in the du directly. And I'll show you more examples of this, as we go forward, for example, next slide. And of course, as always, any antiderivative problem you can check by taking the derivative of your answer. And typically it'll involve a chain rule, because u substitution, as I mentioned, is like a reverse chain rule. And so I've done the derivative down here using a chain rule, and I'm able to get back the integrand. Okay, so I'll let you check that derivative. So this next problem is a definite integral. So I wanted to do a u substitution problem where we had bounds. So on the previous problem, we didn't have any bounds. So as always, I want you to first recognize that this is an integration problem, not a limit problem, not a derivative problem. Second thing is to say, do we just know the answer? Is it an easy problem that we know what the antiderivative is right off the top of our head? In this case, I don't know the antiderivative of root 3 minus 2x off the top of my head. So I need to do something. I need to try some mathematical strategy. The only strategy we really have in Calc 1 is to do a u substitution, or to evaluate the integral using geometry, which I'll talk about in a little bit. So here for the u substitution, what's the theory? The theory is I want to make the integrand simple. And if this 3 minus 2x here, instead of being 3 minus 2x, if it was a single symbol, if this was just the antiderivative of the positive square root of x, I could do that. That I know how to do. We can do that with a reverse power rule, for antiderivatives. So let's make it a single variable using a substitution. So here I simply say, let u equal 3 minus 2x. And then, of course, as is my habit, I automatically calculate du. du equals negative 2 dx. If you look at the integral, there's no negative 2. If I look here at this integral, there's no negative 2 on the outside hanging around that I can, put next to the negative 2. So it's not really a problem. When du differs from dx by a constant, that's never a problem. I can always multiply inside the integrand by negative 2 and then divide by negative 2 and fix that part. And I'll show you that in 1 second here. The other thing here I want to do is, because this integral has bounds, I want to convert the bounds. So specifically here, I take when x is equal to 1, use the substitution. So when x is equal to 1, I'm now using this substitution, u equals 3 minus 2x, and I'm plugging in, 1 for x to solve for the new bound. So here you get back the same number just by coincidence. When x is equal to 1, 3 minus 2 times x happens to also be equal to 1. And here, look, with the other bound, it's not the same. When x equals 3/2, I plug that into here for x. So 3/2 times 2 is just 3. So you get 3 minus 3, you get u equals 0. So let's put this all together. Let me show you now how I use each one of these pieces of information. So here's the original problem. First thing I'm going to do is let me fix the issue with the dx. Okay, I'm missing a negative 2. There's no. So look here. I multiply by a negative 2 and divide by a negative 2. So I haven't changed the value of the integral. I've only made a cosmetic change. It just slightly looks different, but it's not different at all. And why did I do that? Well, now, once I get the negative 2 dx here, I can replace this entirely with du. because the du, if u equals 3 minus 2x, du has to equal negative 2 dx. And so now the next thing I'm going to do, so now I'm going to do all the substitutions. In particular, I'm going to replace this with du. I'm going to replace the bounds with the new bounds in terms of the letter u. And I'm going to replace 3 minus 2x with the letter u. So here we go. And you'll see everything has changed, right? So here's 3 minus 2x I replaced with u. Negative 2 dx is du. The 3/2 became a 0, and the 1, stayed the same, basically. And now this is a successful u substitution because the integral we have now, we can actually solve. If I just write radical of u, positive square root of u as u to the 1/2, I can now use the power rule for antiderivatives. The antiderivative of x to the n is x to the n plus 1 over n plus 1 plus c. So here I get that u to the 3/2 over 3/2 is the antiderivative with the 1/2 that's out in front. Oh, I did one other step here. So I didn't lose my minus sign. I reversed these two bounds. And when you switch your bounds of integration, you get a minus sign, but I already have a minus sign. So the two minus signs cancel. And so now I have a plus 1/2, integral 0 to 1. So you should notice here the bounds have been reversed and I lost a minus sign. Yep, and then I just do the f of b minus f of a. I do the algebraic simplification here. So remember, dividing by a fraction is same as multiplying by the reciprocal of the fraction. So I simplify that and then do f of b minus f of a, and I get the answer as 1/3. So here I also, so two comments. So regarding method 2, if you don't like this part where I put in the -2 and divided by a -2, the other option is to solve for dx. So look, if I solve for dx, then this says dx equals -1/2 times du, or du over -2. And then when you plug it in, you get your du right here. And this -1/2 we pull out and we get it right here. So it depends what method you like. If you like to solve for dx, that's awesome. You can do it that way. Or if you like to set it up to where the integrand, you build up your du. So here by multiplying on the inside by -2 and dividing on the outside by -2, I'm building up dx to look like du. So it just depends what method you like to do. As I mentioned once, at the end of the day, it's probably best to be able to do it both ways. You should be able to do it one way or the other. That's the best, right? If you can do it both ways. So here, I want to show you here a slight variation. So this is, again, the same u substitution, except instead of converting the bounds. So here, I won't convert the bounds at all. So what I'll do is I'll first solve the antiderivative in terms of x. So we use exactly the same u substitution, but I'm solving the antiderivative. What does that mean? I don't have any bounds. I just want to know what the antiderivative is. So plug in, you get the same integral in terms of u. We find the antiderivative. Okay, and so now here's where it's different. Now I'm going to go back to the x variable. So this u, I'm going to replace with 3 minus 2x, the thing we originally substituted for. And so here's my answer for the antiderivative. And so now I'm going to use the antiderivative in terms of x and the original bounds. So these bounds here are the original bounds for the x variable. And again, these are two options. If I don't want to convert the bounds, then I need to go back to the x variable. If I do convert the bounds, so here, if I make this conversion and say, now let me integrate from u equal to 1 to u equal to 0, then I need to stay in the u variable. You see, these coordinates have to always match up. If I'm using coordinates for u, then I have to have an antiderivative in the variable u. If I'm using the bounds or the coordinates, these bounds here for the x variable, then my antiderivative needs to be in the x variable. So again, these are two different options of arriving at the same answer. So here, when I do f of b minus f of a, I get the same answer of 1/3. Just two different styles. As I said, the big mistake I see with students is they'll mix up their u and x variables. They'll use the wrong bounds for the wrong variable. And so that's the only thing, is to be consistent. Do one or the other. Here's a trigonometric problem, an integrand involving trigonometric functions. The point of this example is that, sometimes there may be more than one substitution that'll get the job done. So just something to keep in mind. So for example, in this problem, one thing you could try, and it's not necessarily obvious, but just to let u equal secant, then du will be secant tan dx, and all we have to do, the integrand, is rewrite it. Remember that secant squared is the same as secant times secant. So I write this as secant times secant, and if you look right here, my secant tan dx, that'll become du. And this secant right here that's left over, that'll become u. And so after we plug in, the integral, simplifies drastically. Secant squared tangent x looks so complicated, but it simplifies to antiderivative of u du, which is very straightforward. So we know, using the power rule, we get u squared over 2 plus c. And then last step, I want to plug back in the secant for u, because I want the solution to be in terms of the original variable x, because the original problem is dx. Same problem, but now let u equal tangent. This is definitely more natural substitution, because you can see the secant squareds right there, and the derivative of tangent is secant squared. So if u is tangent, then du is secant squared dx, and the substitution is very straightforward. So I just put the secant squared next to the dx, and now this term will become du. And the tangent here, that'll become u. And again, we get to u du as our very simple form here. Then we take the antiderivative, I get u squared over 2 plus c. I plug in for u, and I get 1/2 tangent squared. So the antiderivative is 1/2 secant squared plus c, and it's also 1/2 tangent squared plus c. We get two different answers, seemingly. So I also did this problem to review the theory of what an antiderivative actually is. It's not a single function, it's a family of functions. And here we're not actually getting two different answers. These answers are equivalent because they're secant squared and tangent squared here essentially are in the same family of functions in this scenario. They differ by a constant. So let me show you. Now I just want to use a trig identity to show you that these two answers are actually the same. So starting from this very familiar trig identity, sine squared plus cosine squared equal to 1, divide both sides of this equation. Okay, I'm dividing the left and right hand side by cosine squared of x. So I divide by cosine squared. And so now sine squared over cosine squared becomes tangent. Cosine squared over cosine squared is 1, equals 1 over cosine squared is secant squared. So we get this identity when you divide both sides by cosine squared, that tangent squared plus 1 equals secant squared. And so now I'm going to use this to show you that the two answers are actually in the same family. So here, our first answer was 1/2 secant squared. Let me replace secant squared with tangent squared plus 1 using this identity. So then I get 1/2 times tangent squared plus 1, the whole thing plus c. And now I distribute this 1/2 to each term. And here I'll have 1/2 plus c. And 1/2 is a constant, c is a constant. So 1/2 plus c will be a new constant that I'm going to call c tilde. And here we get back our other answer. So here's the first answer we got, which was secant squared plus a constant. And here's the second answer we got, which is sorry, 1/2 secant squared plus a constant. And here's the second answer we got, which is 1/2 tangent squared plus a constant. And we see that, here we can make one answer look like the other. So yeah, more than one substitution might work. And also an antiderivative in its purest form isn't one function. It's infinitely many functions. And when we're dealing with trig functions, they may not look the same, because of the identities. So here's another U sub. It's not necessarily obvious what the U should be in this problem, and again, trial and error is part of it. And the more you do U sub, the better it gets. You start to see the patterns just when you look at it. Here, I'm going to be motivated by the same idea I was motivated before, that I want to take this complicated expression, 1 plus root x cubed, and make it simpler. And what would make it simpler is if it was just a single variable cubed. So here, let me try and make the 1 plus root x into a single term in the hope that we can, make the integrand look simpler. So here I say let u equal 1 plus x to the 1/2, and then immediately calculate du. So the derivative of 1 is 0. The derivative of x to the 1/2 we do this power rule. I bring down the 1/2 x to the minus 1/2. I get that du is dx divided by 2 root x, which is exactly what we have in the integral. Here the du looked a little weird. That's why I wanted to do this example. So here, this thing is exactly what appears in our integrand when we move the 2 root x over. So this dx over 2 root x, I replace that now with a du. The 1 plus root x cubed, that gets replaced with u cubed. And now we have something that's easy to integrate using the power rule. I know this is u to the 4th plus 4, and then I replace the u with 1 plus root x because we have to have our solution in the original variable, which we started out with x, so we should end with x. So this next 3 set of examples are very sneaky. And what I want to do is to not just show you easy examples in class, but to show you tricky examples. So this problem is sneaky, but so are we. So here, I'm going to use the same logic that, the x minus 1, if I could just simplify that into a single symbol, dealing with square root of x or square root of a single symbol is a lot easier than the square root of the difference of 2 things. So let u equal x minus 1. Great. Then I solve for du. Du is just dx. And so when I look at the integral, okay, x minus 1 I have, no problem. I'll replace this x minus 1 with u. That's awesome. And the dx, I've got that. There's a dx right here. I'll replace this dx with du. But there's one issue now. There's an x out in front. And so now my question is, okay, what do we do with the x? So this is the slightly tricky part, or just another phase of u substitution that we just have to learn. Here, what I'm going to do is use the substitution to solve for x. If u equals x minus 1, move the minus 1 over, we get x equals u plus 1. So here, I took this negative 1, moved it to the other side, you get x equals u plus 1. X equals u plus 1. And now I'm going to take this x equals u plus 1 and substitute it right in here for this x. And then hopefully, let's see what happens. It'll work. So here we go. Here's all of that. So, keep in mind the x minus 1 I'll replace with u. The dx I'll replace with du. And here, this is a little tricky here. This x I replace with u plus 1. So there's the u plus 1 from the x. Here's my, replace the x minus 1 with a u. And then here's the du. And so now we've converted, one very important part is at the end of our u substitution, everything has to be converted into a u variable. So that's good. And now we reset. how do we solve this problem? So here, we're going to do the algebra, distribute the u to the 1/2 to each term. U to the 1/2 times u to the 1 is u to the 3/2. U to the 1/2 times 1 is u to the 1/2. So that's what it looks like. And now I can go ahead and integrate term by term. I can use the power rule for, antiderivatives on each term separately. So here I use the power rule. And then remember, dividing by a fraction is the same as multiplying by a fraction. So I just simplify the fractions in the denominator. And finally, very last step here, I replace the u variable, this u variable here with x minus 1, and this u variable here with x minus 1, because I want my final answer to be in terms of x. And so then we get our final answer. So this was tricky because we had to do this extra step here, where we need to solve for x in terms of u plus 1. I mean, we typically always do that, but here we had to do a little more work. We had to explicitly solve for x in terms of u. It didn't just kind of fit together nicely. Like in the previous example, we had everything we needed for du, and it just worked out. So here we had to still tweak it a little bit. So this next problem is very similar. I just want you to kind of get used to this idea of kind of this reverse substitution where we also solve for x. So here, again, I'm motivated by the idea of trying to make this expression under the radical symbol simpler. I want to make that into one variable. So I say let u equal 1 minus x, and then automatically calculate du is minus dx. So I do notice one slight problem. In the integral, there's no minus sign. So I have this minus dx. In the integral, there's no minus. That's okay. If du differs from dx by a constant, that's okay. We can always multiply by a minus and divide by a minus. The other problem I noticed that's a little more serious is this x squared. And so here we do our trick. Let's solve for x in terms of u. So here, if u equals 1 minus x, I move the minus x over and I move the u over and I get x equals 1 minus u. And so now I'm going to substitute right in here, this x, I'm going to replace with 1 minus u. Okay, so here we go. There's the original integral. So be careful, I'm going to multiply on the inside here. So I didn't explicitly do this step, I skipped the step, but I'm going to multiply the dx by a minus and multiply on the outside by a minus. The minus dx then, I can replace with du. And I get a minus sign on the outside here. But minus minus cancels that. So I haven't changed the original nature of the information, just what it looks like. And then look what I did in the numerator. I replaced the x with 1 minus u. And in the denominator, I replaced 1 minus x with u. And then we got our du. Everything's converted to the u variable. So now we're in business. And now we can try and solve this problem. Reset. This is now a new anti-differentiation problem. Here, I really hope your algebra vision kicks in and you say, aha, let me square out the numerator because there's math that can be done there. And once I do that, since the denominator is a single term, maybe I'll try and break up the fraction because these are all standard strategies for solving an integral. Especially this thing where you break up the fraction, that's a really good one, So here, let me FOIL the numerator. So I get, 1 minus 2u plus u squared using our a minus b squared formula. And then let me break up the fraction into 3 fractions. I rewrote the denominator as u to the 1/2. And now let me do the algebra. Here you remember x to the m divided by x to the n is x to the m minus n. So here, be careful. This term is right here. So that would be u squared, u to the 2 minus 1/2. 2 is 4 over 2. 4 minus 1/2 is 3/2. And this term is right here. 1 over u to the 1/2 is just u to the minus 1/2. And the middle term is in the middle. U divided by u to the 1/2 is u to the 1 minus 1/2, or just u to the 1/2. And then here I distribute the minus sign. So in this next step, you'll notice this negative symbol here became a positive symbol. That's because I now distributed this minus sign to all three terms. You'll notice the other two terms became negative. I distributed the minus sign and then did the antiderivative. So here to here is my power rule for antiderivatives. U to the n plus 1 divided by n plus 1. Very last step, I bring the fractions out from under the denominators and replace the u's with x's. So again, there's the usual u substitution stuff that we have to do. And in this case, I even have to get this minus sign in there somehow. By the way, if you just solve for dx, you say dx equals negative du, and you get your negative du right away, however you want to do it. But here we have the additional requirement of solving for x in terms of u. That's the extra thing about this problem that I wanted to show you. Okay, one last one here, and then we'll move on to, well, then I've got one more problem. Then we'll move on to some other things. So here, this is finally probably one of the sneakiest versions of this type of problem. So here, again, I want to take the complicated part and make it simpler. So here, x cubed plus 1, that's under the cube root. If that was a single term, I know how to find the antiderivative of just, the cube root of x or cube root of u. So I say let u equal to x cubed plus 1. Do I know that this is x cubed? Do I know this is going to work? I don't. This is trial and error. This may not work. After all this work, we might work it out, get to the end and not be able to do the integral. And then I'd have to, go back and start over again. But this will work, So here I automatically calculate the du. And I notice the du has a 3. There's no 3. That's not a problem. I can multiply and divide by 3. But the du has an x squared. Here I have an x to the 5th. So how do I fix that? Well, let me, we know x to the 5th. I could write x to the 5th as x cubed times x squared. And then I have the x squared. Then this x squared right here and the dx would become my du. And that's great. That, that's progress. But of course, we would still have this x cubed left over, right? And so, the question, okay, so what do we do with this x cubed that's left over? And so now we're going to use the substitution, right? So here it's the same trick. Use the u substitution to solve for x cubed. In this case, if I move the plus 1 over, we can get the equation x cubed equals u minus 1. So I took this plus 1 and moved it over. I get x cubed equals u minus 1. And so now I'm going to replace this x cubed here with u minus 1, and then hopefully we'll see what happens. I mean, at that stage, everything will at least be converted to u. So here are the steps. First, I write the x to the 5th as x cubed times x squared. Then I put the x squared next to the dx here. Put the x squared next to the dx. I also multiplied by a 3 and divided by a 3. Now this entire term looks like my du. And I replace the x cubed plus 1. This x cubed plus 1 will get replaced with u. And the x cubed, I'm going to replace with u cubed plus 1. So this x cubed by itself. So be very careful now. The x cubed became this u minus 1 right here, this term here. And the x cubed plus 1 to the 1/3 became this term right here. And of course, we have our du. Yes, so now we reset. You know, in some sense, we have some success here in that everything is in terms of the u variable. Now it's a new problem. How do we solve this problem? Distribute the u to the 1/3 and integrate. Using the power rule, I get 1/3, all this mess. Then I simplify, I bring the fractions that are in the denominator up and replace the u with x cubed plus 1. And that's the final answer. So, you know, it's difficult if you haven't seen it. If you've seen it, it's a little tedious, but practice makes perfect. And that's really important. The more you practice, the better it'll get, the easier these things get. So we end section 4.5. Oops. So we got one more example here. This is a trig problem. You know, here you have a couple of options. So I'm looking at the integrand. Obviously, I don't know the answer. So I'm going to try a u substitution. And so here you have some options. Here we could let, for example, u equals sine, which you see upstairs. But then that would say du equals cosine. And I don't have a cosine in the numerator. So this is very careful here. You should be very careful. This cosine cubed is in the denominator. Our du would equal cosine, you know, in the numerator times dx. And I don't have a cosine upstairs. So we should try something else. If I let u equal cosine cubed, that's a mess because the derivative is like 3 cosine squared times sine. You definitely don't have that. Here, the trick is to let u equal cosine. Think of the denominator here. Remember, cosine cubed, that's just a composition. That's the cosine function, quantity cubed. So let the cosine inside the cube, let the cosine be our u. Then du will be negative sine dx. And here we have bounds. So I'm going to convert the bounds. And remember how we do that. When x equals 0, I take x equal to 0 and plug it in for cosine. Cosine 0 is equal to 1, so I get u equals 1. I convert the other bound. And so here I'm ready to do the integral. So here's the original integral in the x variable. And now here's the integral in the u variable. So, oh, not yet. So here I did the thing where I multiplied by a minus on the inside and the outside so I can get my minus sine x dx. And I put the sine next to the dx. So this whole term now will become my du. So this became a du. 1 over cosine cubed of x. Think of that as 1 over cosine x, the whole thing cubed. And I replaced the cosine x with u. So I'm at 1 over u cubed. And then here, 0 became 1, pi over 3 became 1/2. And so we have some kind of success in that we've completely converted the integral into the u variable. And we notice we can do the antiderivative. So here, I'm going to flip the bounds here and get rid of this minus sign. So you remember, if you change the bounds of integration, right here, you get a minus sign, but there's already a minus sign. So minus minus becomes plus. And so that's what I do just because I didn't want that minus sign. It was irritating to me. And I wrote the 1 over u cubed is u to the minus 3. And now we're in business, you know. It's just the usual antiderivative of u to the n is u to the n plus 1 over n plus 1. So there's the antiderivative. And then fundamental theorem of calculus says now do f of b minus f of a. And so here I factored out this negative 1/2. So there's this negative 1/2 right here. I factored that out and just did the f of b minus f of a to the u to the minus 2. And then do all the math there, and I got 3/2. So yeah, you know, this one, sometimes the trig functions, you have to try a little bit, play around with it. By the way, with this problem, another way to do this is to rewrite this problem. The cosine cubed, we could have actually factored as cosine squared times cosine. And now 1 over cosine squared is the same as secant squared. And here, sine over cosine is the same as tangent. And the secant squared tangent integral, that's a problem we solved earlier. We actually solved it in 2 ways. You can let u equal secant, or you can let u equal tangent. So you can see with these trig integrals, there's many ways to solve them. You know, using identities or rewriting them. Sometimes going to sine and cosine is a very good strategy when, you know, when it's super complicated. Just go back to the basics. What is it in terms of sine and cosine? So here, let me end up section 4.5. We finally want to just talk about some situations where we can get the integral immediately, either simplify it or get the integral immediately using geometry. So for example, suppose we have an even function. You remember the definition of even, f to the negative x equals f of x. Then if we're integrating from minus a to a, that's the same as integrating from 0 to a and multiplying the value of that integral by 2. And you can see, this is not a proof, but you can see visually this area and this area are always going to be the same, you know, because of the symmetry, or even if it was below the x-axis, the net area on the left and the net area on the right of the y-axis will always be the same. So here we can just integrate from 0 to a and multiply by 2. How does this make life easy? Well, sometimes plugging in 0 is a lot more convenient. Instead of plugging in negative a, when I do my f of b minus f of a, I get to plug in 0, and that's an easy number to plug in. To, you know, sometimes makes life easy. The other scenario is when we have an odd function. So here, if f of negative x equals f of x, and if we're integrating from negative a to a, you can see that the net area on the left and the net area on the right are going to cancel. The net area on the left is, you know, a negative number. It's negative whatever this area is. And the net area on the right is a positive number. It's positive whatever area this is. And when you add the negative number to the positive number, they cancel out. And so for an odd function, if you're integrating from minus a to a, it's just 0. You know, there's no need to even find an antiderivative and do f of b minus f of a. You can do all those things, but it should and will turn out to be 0, you know, assuming we don't make any mistakes. So let me do a couple of examples. So for this first one, find the definite integral of absolute value of x from minus 1 to 1. You know, as you remember, you know, it's a good time to start remembering all these old facts from chapter 1. You know, here, the absolute value of x is an even function. Think about the graph. And so integrating minus 1 to 1, because it's an even function, that's the same as integrating from 0 to 1 and multiplying by 2. But now, and this is kind of helpful, remember that in this integral, the x variable is between 0 and 1. That's what this integral tells us. We're integrating from 0 to 1, and x is between 0 and 1. So in particular, x is larger than 0. So if x is larger than 0, I can drop the absolute value bars. So here, if x is greater than 0, or, you know, greater than or equal to 0, then that means the absolute value of x, I can drop the absolute value bars. And now I've simplified the integrand. Now the integral just looks like the integral of 2 times definite integral 0 to 1 x dx. You know, and then I finish up, find the antiderivative, f of b minus f of a. So here, you know, it helped us in that we didn't have to split up the integral. We could just do one integral, and we were able to immediately drop the absolute value bars once we got x to be between 0 and 1. So this problem I really like because it looks complicated, but it's a trick. You know, students will try to do u sub and all this kind of stuff. But if you look at the integrand, f of x, and check, f of negative x here, the negative x squared is just x squared. Negative x to the 6th is just x to the 6th. But sine of negative x is an odd function. Sine of negative x equals negative sine of x. And here it turns out the integrand is an odd function. And so when you integrate the odd function from minus a to a, in this case, minus pi over 2 to pi over 2, the answer is 0. You know, here it's important not to fall in the trap. to try and do a U substitution or to try and do some other long drawn out math and waste our time. Here we have to realize the integrand's too complicated and weird looking. You're integrating from minus a to a. There must be more to this. Let me check, is the integrand odd or even, you know? So let me finish up really quickly. The final technique for solving integrals is to use geometry. So here we've reversed the process. Before we use the integral to find the area. Now I'm going to find the area to evaluate the integral. For example, with this integral, it's very difficult. We don't know how to find the antiderivative of just square root of 9 minus x squared, positive square root of 9 minus x squared. So here, let me think about what's the graph. What does the graph of this function look like? Okay, so first I'm going to give it a name. I'm going to call it y. Let me just set it equal to y. And let me try and work backwards and just do some kind of exploration and see where did this y come from? So here, if I square both sides, I get y squared equals 9 minus x squared. If I move the minus x squared over, I get x squared plus y squared equal to 9. And this is a circle of radius 3. You see this letter y right here is the same as the y right here, which is the thing we're integrating. So the thing we're integrating is coming from a circle. It's the y values from a circle. So here, if you look at the circle, in fact, it's the positive y values because this is a positive square root. If there was a minus sign in front of it, it would be the negative square root. And then we'd be looking at the bottom half of the circle if there was a minus sign. But because this is a positive root and we showed these y values are coming from a circle, we conclude the graph here is a semicircle, the upper half of a circle from minus 3 to 3. This is not easy or obvious. If you haven't seen this before, this is something to look at and think about. And then at the end of the day, it doesn't hurt to just memorize that the graph of square root of a number minus x squared is you know, the upper half of a circle. You know, it'll come up in Calc 2 also, or learning this procedure. So now I'm just going to calculate the area using geometry. I know the area of a circle is pi r squared. The area of half a circle would be pi r squared divided by 2. And here the radius is 3. So I have pi times 3 squared over 2, or 9 pi over 2. So here we did no integration. That's you know, the thing to keep in mind. So I've got one more example to do, but my time is up. So I'm going to stop right here and I'll do that last example on